Hello, welcome. So today I'd like to work on this little register right here. What I'd like to do is take a little bit of a break from the VDP series that I've been working on and do some improvements to the CPU. And one thing that is bothering me is, well, you can kind of see it right here. There's no way to encode 16-bit immediates. But I have an idea for how to add that, and that involves the register that you see right here. So let's jump right into it. Okay. So the main issue, and where I'd like to do some improvements right now, is in here. So currently we have 4-bit immediates, which is a little bit small. I might try and fix that. We have 6-bit immediates, 8 bits, and 11 bits. So it would be nice to be able to use a special instruction with those 11 bits that can then be used on the other instructions that might take either just 8 bits or 6 bits or 4 bits. So in order to do that, I think it makes sense to have a register that saves those 11 bits for the next clock cycle, or in other words, the next instruction. And then that instruction can use those bits as its upper bits. Doing so is going to be a little bit tricky though, because it needs to be inserted into this mess somehow. And I'm not sure the best way to do that. Probably the easiest way is to insert it right here and just say that the Imm instruction contains the upper 11 bits of whatever. So it'll always be just the upper 11 bits, and the lower 5 bits, I guess, will come from the current instruction, and it'll ignore the other bits in the current instruction. So I think that's going to be the most straightforward, so that's what I'm going to do. So basically like this. So we'd have the Imm register, and that has 11 bits in it. We split the immediate tree, I guess you could call it, or the immediate mux. We have 16 bits coming out of that because of the sign extension. And then the first 5 bits here, so 5 bits, just goes straight through. That will always be the 5 bits that end up going into the rest of the processor. But for the upper 11 bits, so we've got that split off here, and then we have it merged back here. That goes through a mux, and this needs to be 11 bits. And the mux decides, do we take those 11 bits from the instruction itself, which will be mostly sign extension bits for most instructions, or do we take it from the immediate register? And if we take it from the immediate register, then that will just simply replace those 11 bits in the instruction. Now you'll notice that there's a register down here that's tied to the select line, and this is going to temporarily store whether or not the current instruction had an immediate instruction just prior to it. And if it did, then it'll modify that instruction. So I'm going to continue trying to wire this up. So in theory, this should work. So what I did is, in the instruction decoder, it's easiest just to actually check, is this an Imm11? And there's only 4 instructions in that class. So I'm just checking if it's the first instruction, i.e. 00, and just outputting a signal saying it's an Imm op. Then here I'm taking the Imm op and I'm passing it into the enable on the Imm register. And I'm also passing it into this D flip-flop to save that state for the next cycle. And then, of course, the next instruction most likely will not be an Imm instruction, and so this will go back to false. And then on the cycle after that, it'll go back to the regular settings. So I think this will work, which is pretty exciting. It's a fairly small change. So let's look at our cpudef, because I have a feeling it's going to throw a monkey wrench in things, and we might have to fix some stuff. So here's our cpudef, and I've been making a few changes because I'm trying to support C compiler, and some of them is just having some aliases for the registers. And I started adding some macros for various pseudo instructions. So for example, sign extend is just the shift left and then arithmetic shift right by 8 bits. That just makes the 16-bit register have a sign extended 8-bit value in it. And these are just aliases for making the ,0 optional for these instructions. So what makes a macro is this ASM here, and it allows you to write assembly in there. Some parameters need to have the curly braces around them and some do not. And so it's kind of just a trial and error thing. If it doesn't work without them, then try adding the curly braces around the variable and it should work. I'm not sure I fully understand the rules on that. Okay, so the jump and the call instructions are in the same group. So we should be able to actually just take this. Now we could just leave it at this, but this is the upper 11 bits. So it might be helpful to specify that. So I believe the way to do that is this. So I don't think I need this here. Let's just make sure that this compiles first. Ah, it's not like that. Okay. Sorry then, I guess. That worked. Okay. All right. So one of the issues then is it would be nice to have some macros for each of the different instruction formats. And in those macros, then we can put the asserts required to make sure that it'll select one form of the instruction versus another form with the immediate instruction prepended. So this is what I've got so far. I've got a instruction for each of the formats, and all I did was copy the instruction format up here so that, yeah, this should be a good building block to use in these other instructions. And then I started copying out the magic value here for the op and put it up here. You'll notice that some of these have an I in front. That's because the op is different between the immediate and the non-immediate. So I think that should do. And this subrule def means that it can only be used within the instruction, like as a parameter like this. So then it's better than a constant in that way. It doesn't pollute the global namespace. So I think next would be convert some of these instructions and see if they still work. So let me do that. It does indeed appear to work. I was just replacing the jump instruction with the new format indirection here, and that works fine. So let's continue. So this is interesting. I built a test case to test the emulator, and it basically just runs all of the test programs. And I'm using that to verify that I haven't made a mistake here. And actually, I can't tell where the mistake was. It's in this line because I've been testing after changing each one. And I'm doing the FUMT RI8, which is what the move with immediate is. So it's this one here. And I can't tell the difference. Let me just back out of this edit here. So this is the original. Let's just duplicate that here. Okay. So this should be equivalent because I'm just using RI8 up here. So let's copy this. So up here is move I should be 0. So if we do this, tests pass. If I do this, tests break. Yeah, I'm quite stumped. I'll be back. I figured it out. I had it like this, and that's incorrect because this doesn't have a type. It doesn't have a type suffix here. And specifically, it doesn't have a type that is a subrule def. So I think that's what the rule is. You only need to use the curly braces if this is a subrule. So in this case, if I go like this, then everything passes. So, okay, all right, I will continue then. Okay, so this is what I got. I guess I'll go up to the top here. I've got these. I had to split these out. So these are immediate forms and these are non-immediate forms. That's there. And then the formats, I had to make a bit of a fix in the ls format. I was using Imm here, but I specified it's a register, which it's not. I also changed it to value to be consistent with the other formats. And then, yeah, all of the instructions have their format, their op, and whatever parameters they take. And this seems to pass. So awesome. So the next step would be to have the option to prefix these instructions with an immediate instruction if the value is over what can be contained. So for example, the ls format, which is load and store, the value can only be a 4-bit value. And if it's outside of that range, you need to use an immediate instruction or an Imm instruction as a prefix to extend that. And there's going to be bugs with that because the immediate is only a 4-bit value. I have some ideas on how to fix that, but for all of the other instructions, we should be able to do that. So I'm going to try doing that. Okay. So what I did was just split the Imm RI6 format apart into 2 different variants. So in custom ASM, you're able to have 2 different listings for a single instruction, and then you can use assert statements to tell the assembler which one you would prefer. So if the assertion fails, then what it'll do is try and find another one. If it can't find a different instruction where the assertion passes, then it will error out and it'll give you an explainer for why it failed. If there are multiple instructions that have assertions that pass, it'll prefer to use the shorter one. In this case, what I'm doing is I'm checking to see if the value fits within the range that's valid for the instruction. And if it doesn't, so if it is greater than a 6-bit number, so that's what this is trying to ask. And I'm saying a 6-bit signed number. So that's why I'm not looking at the 6th bit. So it just looks at the lower 5 bits and it says, okay, is value in that range of a signed 5-bit value? If it is, then it'll just use the regular instruction. If it isn't, then what it'll do is it'll assemble an immediate instruction, then the regular Imm RI6. So this is what I came up with. I need to do that for these, but in the meantime, what I've done is I updated the emulator so that I can run the tests, and the tests should pass, and they do. What I did is I created a test case that tests all of the various different scenarios. So in this case, it's moving the Imm, which should be the upper 11 bits of this number here, and then it's joining that to a 0 that it's putting into R3. So that should effectively zero out the bottom 5 bits. So what I do then is invert it by XORing with -1, which is all Fs. It's the same as this. And then what I do is check if it's not equal to all ones, because that's what should happen, right? If it removes the bottom 5 bits and converts them into 0 in this, then when you invert it, it should be all ones. And I did this to check using instructions that don't require an immediate prefix to make sure that that part is working. And then I incrementally added these other test cases. So this one is constructing a 16-bit value using existing instructions that don't need the prefix, but this one might be problematic. So I should probably convert that to 7. And then it just ORs those 2 numbers together and then checks to make sure that the expected value is in there. And this will use the immediate prefix. So if you see in the instruction stream, this is just the output from the emulator. So you see it becomes 2 instructions. The first one has the upper 11 bits and the bottom one has the rest. And then it's checking if it's this number here. And then I'm trying augmenting the add instruction. And then I'm trying an edge case here because 63 fits into 5 bits, but the sign bit is set. So that needs to be handled. Otherwise it'll become -1, which is not correct. One thing that we need to fix in the circuit though is this case here. So if we have an add instruction that's being skipped by an if instruction, and that add instruction has an immediate instruction before it, that can cause all kinds of problems. So we need to be able to skip 2 instructions in this case if there's an immediate instruction there. That's going to be tricky. So what we need to do is check to see if we're trying to skip an immediate instruction and then don't clear the skip flag. So that'll require adding a bit to the microcode to indicate that it's an immediate instruction and then putting that bit into the skip logic. So let me do that and set up the test case within digital so that we can check that everything is working. Okay, so this is what I came up with. There's an extra bit in the microcode ROM called Imm, and I just added it to the microcode. So if we look at the microcode, here's the Imm flag on the Imm instruction. Otherwise, the Imm instruction doesn't need to do anything because it was already handled in the decoder. And here's the Imm bit, and that ends up being right here, the 14th bit. And then that runs over here to this AND gate. So if we're skipping the current instruction, and this current instruction happens to be an immediate instruction, then that goes into this OR gate and it tells it, okay, skip the next instruction too. And that seems to work. I have a test case that passes. So let me just show that. So in our test suite, there's now the Imm test. And if I run it, it passes. Where is it? This one passes. There's a long-standing bug with load store causing that to fail. And I don't really feel like fixing it right now, but that'll definitely need to be fixed in the future. I'm going to be doing some work on that circuit fairly soon because I want to add byte-wise addressing to the data bus, but I don't want to do that today. So we've got a passing test case. All right, going back to the cpudef, I just need to do the same thing here for the rest of these instructions. Basically, everything but the instruction that has no immediate should have forms to do this. So let me do that. So I have updated these, and it's a very similar structure to these ones here. The difference being that the number of bits is different, so depending on the size of the immediate. And then we have this one, and I'm not 100% sure this is working properly, but I'll get to that in a moment. And then we have this. So I have a confession to make. Sometimes what happens in software development, and I guess also in electronics, is something known as a yak shave. And basically the story goes that you set out to do something, and one thing leads to another, 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 and then you find yourself shaving a yak. And I have found myself shaving a yak, unfortunately. And if you don't know where that comes from, feel free to Google it. But yeah, so there's now another instruction format. Yeah. So this is the old one. And you can see here, there's only a single instruction that's 11 bits. But the problem with this, 4 plus 11 is 15, not 16. And so the load and store instructions can't use the immediate instruction because there's going to be a gap of 1 bit. So the solution to that is either figure out a way to get 5 bits of immediate on the load store instructions, which I don't think is possible, not without a lot of rework. Or I could make the immediate instruction take 12 bits. And actually that can work because I have no idea what to put in this instruction slot here. I put sys because maybe it could be a syscall instruction, but probably not. And even then, like the syscall instruction doesn't need an 11-bit immediate. So yeah, given that, we could use 2 instruction slots for the immediate instruction and then get a 12-bit immediate, which is what I've done. So here's the new one. And you can see here the Imm instruction now has its own instruction format and it has 12 bits, whereas the rest in this format have 11 bits. And that neatly solves the problem of needing an extra bit for the load store instructions. But one thing led to another, and while I can get it to pass in the emulator, I cannot get it to pass in the actual circuit itself. So if I run these, we already know the load store is going to fail. That's fine. The immediate, though, also fails. And what's weird is that if I go to the front panel, I've loaded that program into the CPU. And if I step through it step by step, it halts. So this is successful. No problem. But if I stop it and then I run it again and then I run it at full speed, it hits an error. Yeah. So one thing that I've noticed is that this debugging interface that I've built is not really good. And the main reason for that is now it's nearly impossible to debug this thing at full speed. Here's what the problem is. If I go through here step by step, it takes roughly 15 cycles to update the program counter here because the program counter is coming through the debug bus. So I'm getting bit. Let's see. Maybe it's more like 30? Yeah. 24, it looks like. Yeah, 24 cycles. It takes 24 cycles to update the outputs here. So that's really not helpful at all. I can get some things on here. So memory register file. So I can see the contents of the register file. Actually, that might be useful. So what is the register file doing when we hit the error? Register file? Yeah, R3 is 0, but it's supposed to be 1, 2, 3, 4. That's what the bug is. So here, I'll show you where the bug is. If we go into here, this is the instruction that has the bug. And I'm loading with an immediate prefix, and it should work. And it does in the emulator, and it does if the processor stalls, but it doesn't when it runs at full speed. And I tried putting a NOP in here, but that doesn't help. There will be an immediate instruction right before this. What I'd be curious to see is what's happening to the Imm instruction. So see if we can add some probes or something. So in here, this has changed a little bit. Mainly in here where I've got it checking to see if this bit is set, and then that's the immediate op. And then in here, I had to add in the enable in order to get stall to work properly. So these need to be enabled. So this was turned into a full register rather than a D flip-flop because it can't change its state until it's enabled to change its state. It still pulls the ImmDo, and I don't know if this is correct. It may not be. Actually, I wonder if that's where the bug is. So I think what the bug is, and I just had a thought. I think what the bug is the fact that load stores take multiple cycles. So if it's busy, not stalled, or it's busy, it's not skipping, so I don't think I need to worry about that. Not busy. I might want enable fetch. Let's try it. So here I'm sending in the regular enable for other registers, but let's try putting in the in fetch. That worked. That worked. Let's see if it works in the test suite. Now, I'm almost certain there's going to be bugs from doing that change, but it worked. So I have it working. I can go over some other changes that I did, I think. Let me just try and remember what all of them were. Oh boy. Okay, so I don't think there was any changes in here other than the fact that I'm now using the enable fetch because I need the not busy. Actually, that does make sense. I think that would be bug free because if you think about it, you don't want that register to update until the next instruction. So that's basically what enable fetch does. Yeah, I think that's correct. Yeah, I'm pretty sure that logic is correct. Awesome. Okay, sweet. So I'm getting the last 12 bits here and going into the immediate instruction. Again, it's being enabled by this logic here. Yeah, I think those are all of the changes that I've made in the actual circuit. And then I changed these, specifically these two here. And you see there's no Imm in here anymore because it is its own format. So it didn't need to put an op in there. So the op is kind of just right here, really. Instead of taking the bottom 5 bits, it takes the bottom 4 bits. And so a few changes needed to happen for that. I also had to update the microcode. So if I go into the microcode, here's the changes here. So in this part of the address space, I moved the jump to 0, and then Imm is going to be 1 and 3, and then call is here. Because these are still decoded as I11 format, but Imm takes up 2 slots for the least significant bit to have a place. So that's how that's implemented. So everything seems to be working. All the tests are passing. Load store is still broken. I will fix that in the future. So I think that's it. So thank you very much for watching. I hope you have a great day. Bye.